Numbers are integral part of our day-to-day life, which are typically represented using 10 digits. This is partly influenced by the presence of 10 fingers on our hands, which is reflected in the number systems across several cultures in the world. Formally, the number system with 10 digits is called the decimal number system. We have to represent infinite numbers in the number system using just these 10 digits. To do that, we reuse the digits in ascending order and create unique digit patterns which are lexicographically ordered like the words in the dictionary. Now that we have digit pattern for 10, let's write the pattern for 11, which comes right after 10. So that would be 1 followed by 1. So 12 would be 1 followed by 2, and so on and so forth. To get the mathematical intuition of the decimal number system, let us assign weights for each digit and understand how a specific digit pattern corresponds to a specific number. Let us consider the digit pattern 435. The first digit has the weight 10 to the power 0, second 10 to the power 1, and third 10 to the power 2. Now, I'm just going to add those values by multiplying one with the other. So I end up with 400 plus 30 plus 5. So that is 435. To appreciate what you just learned, let us look at a number system that uses only 2 digits, the binary number system, which is used by the computer, phone, or tablet on which you're watching this video. Computers use two signals, on and off, which are represented as digits 1 and 0. Let's see how computers use these two digits to represent infinite numbers. We start out with 1, 0, 1, 1, and as we run out of options, we go for 1, 0, 0, 1, 0, 1, 1, 1, 0, and so on and so forth. So they correspond to the actual numbers which I'm listing down below. The binary number system is pretty similar to the decimal number system. The only difference is the weights of the digits are in the powers of 2. To get this concept, let's try to work with a binary digit pattern of 101. Okay, so we have the binary digit pattern 101. Let's try to see what number this pattern corresponds to. So the first digit weight is 2 to the power 0, second one is 2 to the power 1, and the third one is 2 to the power 2. Now let's try to evaluate the actual underlying numeric value. So I do it by multiplying the weight with the digit and adding all of them together. So I have 4 plus 0 plus 1, which is 5. Let's see how we can convert decimal number into a binary number. There are numerous ways to do it. I'm showing you one such technique. So let's find out the binary pattern for 4. So I'm going to divide 4 by 2, and then I get 2 with a remainder of 0. Okay, so I'm going to repeat the same stuff over and over again till I end up with either 1 or 0. Okay, so 2 divided by 2 is 1, 0. Because I hit 1, I'm going to write out the pattern right away. So it's 1, 0, 0. So 4 corresponds to 1, 0, 0. To make things clear, let's try it out with 6. Okay, 6 divided by 2 is 3. Okay, so I'm going to write out there, and the remainder is 0. Again, like 3 divided by 2 is 1 with a remainder of 1. So because I hit 1 here, so I'm writing the pattern right away. So it's 1, 1, 0. All right, so with this last example, we're going to solidify our understanding of decimal to binary conversion. So 11 divided by 2, I have 5 with the remainder of 1. 5 divided by 2, I have 2 with the remainder 1. 2 divided by 2 is 1 with the remainder 0. So I'm going to write out the pattern. It's 1, 0, 1, 1. So 11 corresponds to the binary pattern 1, 0, 1, 1. Now if you want to verify if this binary pattern is equal to 11, we could apply the binary to decimal conversion. Okay, so we do that by giving out those weights for every digit in that binary number. Let's add them up to see if they correspond to 11. So I have 8 plus 2 plus 1, which is 11. Okay, so this gives you the basics of binary numbers in general.